What if I told you that the key to understanding complex scientific concepts is hiding right inside the fantastical world of Pokémon? I'm Chuka, but in this scientific safari zone, you can call me Professor Baobab. Welcome to episode 10 of Poke A Mon. Which Pokemon will enter Hooper's portal into the scientific dimension this week? Quick disclaimer, this podcast is not affiliated with the Pokemon Company, Game Freak, or Nintendo. I'm here to use the storytelling power of Pokemon to unlock the marvelous mysteries of science. Dive into Frontiers of Pokemon Research, a free ebook that reimagines your favorite Pokemon as subjects of scientific discovery. Is Pikachu's 10 million volt Thunderbolt deadly? Why is Eevee's DNA unstable? How come Mega Charizard X is blue? It's all here. Sign up for my weekly newsletter and I'll send you this exclusive journal to spark your imagination and ignite your curiosity. Don't miss your passport to a world where science and fiction collide. What's up, Science Squad? Professor Baobab here. And if you've ever wondered why diamond is famous for being the hardest known substance, and whether anything could be harder, you've come to the right place. Today, I'm going to talk about crystallography. I'm going to start with a definition, give a brief account of the history of crystallography, and review its importance. What are crystals and how do they form? I will also answer these questions. Lastly, I will mention some of the allotropes of carbon because it allows me to talk about the structure of Steelix in a way that makes the Pokédex entries for Steelix much more plausible. As I did last week, I will first explain what crystallography is. Then I will explain how scientifically plausible Steelix's Pokédex entries are. What is crystallography? Crystallography is the branch of science that examines the arrangement and bonding of atoms in crystalline solids, as well as the geometric structure of crystal lattices. Crystallography has profound implications across various scientific disciplines. It enables us to understand why diamonds possess their renowned hardness and luster, and why substances like salt dissolve readily in water. The techniques of crystallography extend beyond naturally occurring crystals. Scientists can crystallize a wide array of materials, allowing for the exploration of complex structures, such as those of biological macromolecules. This capability has been instrumental in fields like virology, where understanding the crystalline structures of viral components aids in the development of medical interventions. How did we get here though? The journey began in the 17th century, when natural philosophers like Johannes Kepler and Robert Hooke marveled at the symmetrical beauty of snowflakes and crystals, and wondered what the underlying order that gave rise to such forms could be. Their reflections laid the groundwork for a more systematic study of crystal structures. In the 18th century, French mineralogist René Jussieu, often referred to as the father of modern crystallography, made significant strides by studying the external forms of crystals. He proposed that crystals are composed of orderly stacked units, and he introduced the concept of a repeating lattice structure. The 19th century witnessed further advancements. Auguste Bravais in 1850 derived the 14 distinct lattice structures, now known as Bravais lattices, which describe the geometric arrangement of points in space. This period also saw the classification of crystals into 32 point groups, which were classifications of symmetry. A monumental leap occurred in 1895 when Wilhelm Conrad Röntgen discovered the X-rays, a form of electromagnetic radiation capable of penetrating solid objects. This discovery earned him the first Nobel Prize in Physics in 1901 and paved the way for exploring the internal structures of materials. Building on this, in 1912, physicist Max von Laue, along with his colleagues, conducted pioneering experiments demonstrating that X-rays could be diffracted by crystals. This experiment not only confirmed the wave nature of X-rays, but also revealed the periodic atomic structure of crystals, marking the birth of X-ray crystallography. Subsequently, Sir William Henry Bragg and his son Sir William Lawrence Bragg formulated Bragg's law, which provided a mathematical framework to interpret X-ray diffraction patterns. Today, we have many more characterization techniques such as scanning electron microscopy, energy dispersive X-ray spectroscopy, and atomic force microscopy. In the realm of geology, crystallography is indispensable for identifying and characterizing minerals. By analyzing the crystal structures of geological specimens, geologists can infer the conditions under which rocks and minerals formed, providing insights into Earth's history and the dynamic processes shaping our planet. Crystallography also serves as a cornerstone in materials science by facilitating the design and development of new materials with tailored properties. By elucidating the atomic arrangements within materials, scientists can predict and modify characteristics such as strength, flexibility, and conductivity. This understanding is crucial for advancements in industries ranging from aerospace engineering to consumer electronics. In biological sciences, crystallography has been transformative in revealing the three-dimensional structures of biomolecules, including proteins and nucleic acids. Determining these structures enhances our comprehension of biological functions and processes, such as enzyme mechanisms and genetic replication. Notably, the exposition of DNA's double helix structure was achieved through X-ray crystallography. And we all ought to know how much of a milestone in molecular biology that was. Even the technological applications of crystallography are vast and varied. In electronics, understanding crystal structures is essential for the fabrication of semiconductors and the advancement of nanotechnology. In the pharmaceutical industry, it aids in drug design by revealing the structures of target molecules, enabling the development of more effective therapeutics. Crystallography also contributes to the development of novel materials with specific optical, magnetic, or mechanical properties. Clearly, crystallography is driving innovation across multiple sectors. Now that we have an idea of what crystallography is useful for, let's go deeper. What are crystals and how do they form? Crystals are solid materials characterized by an ordered arrangement of atoms, ions, or molecules that repeat periodically in 3 dimensions, forming a structure known as a crystal lattice. This regularity imparts unique physical properties to crystalline materials, such as distinct cleavage planes and characteristic optical behaviors. The fundamental repeating unit within a crystal is termed the unit cell, which, when replicated in all spatial directions, constructs the entire lattice. Crystals are systematically classified into 7 crystal systems based on the geometries of their unit cells: cubic or isometric, tetragonal, orthorhombic, hexagonal, trigonal or rhombohedral, monoclinic, and triclinic. Each system is defined by specific axial lengths and interaxial angles. For instance, the cubic system features 3 axes of equal length, intersecting at right angles, exemplified by minerals like halite and pyrite. In contrast, the tetragonal system has 2 equal axes and a third axis of a different length, all perpendicular to each other, as seen in zircon crystals. The orthorhombic system comprises 3 unequal axes intersecting at right angles, characteristic of minerals such as olivine and aragonite. The hexagonal system includes crystals with 4 axes, 3 of equal length intersecting at 120 degrees in a single plane, and a 4th axis perpendicular to this plane, differing in length, typified by quartz and beryl. Understanding these crystal systems is essential in fields like mineralogy and material science, as the internal symmetry and lattice parameters of a crystal significantly influence its external morphology and inherent physical properties. Crystallization is the process by which a solid forms from a liquid or gas, resulting in a structured arrangement of atoms, ions, or molecules. The conditions under which crystallization occurs, such as temperature, pressure, and cooling rate, are crucial in determining the size, quality, and properties of the resulting crystals. When crystals are formed, they can also be referred to as grains. The temperature at which crystallization occurs significantly influences the crystal structure and size. For quartz, silicon dioxide, crystallization typically occurs at temperatures between 600 degrees Celsius and 700 degrees Celsius. At these elevated temperatures, silicon dioxide exists in a molten state, allowing atoms to arrange in a crystalline lattice upon cooling. However, rapid cooling can lead to the formation of amorphous silica, such as glass, due to insufficient time for the atoms to organize into a crystalline structure. Since it has no ordered repeating lattice structure, we wouldn't call glass a crystal or crystalline. Pressure also plays a significant role in crystallization. In natural settings, quartz crystals often form under high pressure conditions within the Earth's crust. These conditions facilitate the dissolution of silica into a fluid phase, which then precipitates as quartz crystals upon changes in pressure and temperature. In laboratory settings, controlled pressure environments can be used to synthesize quartz crystals. The rate at which a molten substance cools profoundly affects crystal formation. Slow cooling allows atoms to arrange into larger, well-formed crystals, while rapid cooling results in smaller crystals or amorphous materials. For steel, slow cooling from the molten state can lead to the formation of large, well-formed crystals in pearlite, whereas rapid cooling or quenching can result in the formation of martensite with small crystals. Carbon exhibits remarkable versatility, forming several allotropes, distinct structural forms of the same element, each with unique properties and applications. Among these, Graphite, graphene, and diamond are particularly noteworthy and will be expressly useful for our discussion on Steelix. Graphite consists of layers of carbon atoms arranged in a hexagonal lattice, with weak van der Waals forces between the layers. This structure allows the layers to slide over each other easily. This explains why graphite is an excellent conductor of electricity and heat, as well as an excellent lubricant. Its ability to withstand high temperatures also makes it suitable for use in high-temperature crucibles and as a moderator in nuclear reactors. Graphene is a single layer of carbon atoms arranged in a two-dimensional honeycomb lattice. It exhibits extraordinary electrical, thermal, and mechanical properties, including high electrical conductivity, exceptional tensile strength, and flexibility. Graphene's unique characteristics have led to its exploration in various fields, including electronics, energy storage, and material science. For instance, it holds potential for use in high-performance transistors, supercapacitors, and lightweight composite materials. Diamond is a three-dimensional network of carbon atoms, each bonded to four others in a tetrahedral arrangement, resulting in an extremely hard and transparent material. Its hardness makes it ideal for cutting, grinding, and drilling applications. Diamonds also have excellent thermal conductivity and are used in high-performance heat sinks. Beyond industrial uses, diamonds are prized as gemstones in jewelry due to their brilliance and durability. Now, let's talk about Steelix. I'm going to state the Pokédex entry and which game or games it belongs to. I will then analyze the entry. Finally, I will render my verdict, deciding whether or not the entry is logical or scientific. The Pokédex entry from Pokémon Go states, its body has been compressed deep under the ground. As a result, it is even harder than a diamond. The claim of a material being harder than a diamond obviously requires scrutiny. Geological compression does create fascinating material transformations, and there's scientific evidence for the idea that prolonged underground pressure could alter a crystal's physical structure. When we consider material science, compression can indeed change a substance's molecular structure. Diamonds themselves are formed under extreme pressure deep within the earth, so the concept isn't entirely far-fetched. The entry suggests Steelix's body undergoes a similar process with prolonged underground compression, creating a material that surpasses diamond in hardness. What makes this intriguing is the potential for nanostructural changes. Compression can create unique crystalline structures, potentially introducing lattice defects or creating nano-twinned regions that can double hardness and increase strength and toughness. The idea that a living organism could develop such properties through environmental adaptation is compelling from a speculative biology perspective. Twinning is a phenomenon where crystals can grow symmetrically from a common crystal plane in separate directions. The boundary where the crystals begin to grow out from can be much stronger and harder than normal. Nanotwinning is the twinning of nanoparticles and has been successfully achieved in an attempt to create a substance which is harder than diamond. I have linked the paper published in Nature concerning nanotwinning in diamonds in the show notes. Verdict: scientifically plausible. We now know of substances that are harder than diamonds thanks to innovations in material science, specifically nanomaterials. The Pokédex entry from Pokémon Pearl, Y, and Shining Pearl states, It chews its way through boulders with its sturdy jaws. Its eyes can see in the darkness underground. The claim about chewing through boulders is remarkably consistent with the material properties we understand about Steelix. Its jaw strength would need to be exceptional, far beyond typical biological constraints. Let's suppose Steelix generates compressive forces exceeding 100 gigapascals, as this would be enough to tunnel effortlessly through solid bedrock and potentially crush materials as hard as diamonds or boron nitride. For reference, the animal with the strongest bite force, the Nile crocodile, can only achieve 30 megapascals, a number that is 3,000 times smaller. These extraordinary compressive forces arise from its unique exoskeletal structure. The nanotwinned diamond-like composition provides incredible structural integrity, allowing mechanical forces that would shatter most biological structures. Essentially, Steelix's jaw is a geological drill capable of fashioning the underground of Sinnoh. The underground vision claim is more speculative. The entry hints at a sensory system adapted to complete darkness, potentially involving electromagnetic or seismic perception that goes beyond traditional visual processing. Given Steelix's metallurgical nature and its ability to generate significant magnetic fields, its vision might be more akin to a complex electromagnetic sensing system than traditional light-based sight. Verdict: plausible, although seeing in total darkness seems more poetic than scientific. The Pokédex entry from Pokémon Legends Arceus states, "This Pokémon evolved through use of a strange item. Its body is coated with steel powder and notably hard. Not even a diamond can leave so much as a scratch." The entry claims Steelix evolved through a strange item, which we now know is the metal coat. The metal coat is probably some kind of special metallic alloy with unique properties. We also know that the transformation mechanism is precise and specific. The metal coat isn't a simple surface treatment, but a complex molecular interaction. Its nanoscale lattice interacts with Pokémon possessing metallogenic, as in metal forming, genomic pathways. For Onyx to become Steelix, prolonged contact with the metal coat must occur in the presence of a strong alternating electromagnetic field, typically provided during a Pokémon trade. The alloy's metal ions could act as transcription factors, penetrating the Pokémon's mineralized body and binding to specific genomic regions that regulate metallogenic pathways. This could trigger changes in protein synthesis, favoring metal deposition. However, Pokémon transformed using metal coat are likely weaker and softer than their organic counterparts because they were not formed by geological pressures and temperatures. As a result, it is highly unlikely Steelix transformed via metal coat can be harder than diamonds, since the metallic and ionic bonds found in iron compounds are not as strong as the covalent bonds found in diamond and graphene. Verdict: scientifically implausible. Also, it is unlikely Pokémon treated with metal coat will survive as well as those that develop naturally. Metal coat is kind of like anabolic steroids in the sense that they help speed up development dramatically, but the development is just for show and is not functional. I can practically see you shining out there with all that new information you now have. Now, I could have easily steered the direction towards metallurgy, which is the study of metals, or magnetism, since a lot of the Pokédex entries were referring to iron. a magnetic metal. If you want me to make an episode on either of these topics, let me know. Science Challenge! Before our next episode, I want you to turn on a light bulb above your head. There's no light underground, and they have lived underground since the time they were still Onyx. So why do you think Steelix has eyes? Email me your findings and I might call out your name in the next episode. My email address is chuka1000@hotmail.co.uk. It's also in the show notes. What did you think? Isn't the power of science simply amazing?